I thought, oh, what will I do? And I thought, oh, I'll do an oscilloscope. No one's ever done that before, and now I know why. Yeah, it's nowhere near as easy as you think it is. And hello, it's nowhere near as easy as you think it's going to be. And it was an interesting exercise, actually. So the thing with an oscilloscope and a radio is, if you do a TV, you look at the circuit, there will be certain parts of the circuit with the horizontal output, vertical and sync and all that, and I'll actually show a picture of the oscilloscope pattern that you would expect at that particular stage. And so you've got a reference point, whereas with a radio you don't. You can measure the voltage, you look at the circuit will tell you what the voltage is supposed to be, so you've got a reference point. With an oscilloscope there's no reference point, so you have to know what signal to expect at that particular point. So in your mind, you really have to know what that radio is doing and what you expect the picture to be on the scope. Now, the thing about a radio, and the good part of it is, it's not as complicated as a TV by any means, and you can virtually work the whole scope through the radio just on the principle of using a sine wave. So you start off with a sine wave, and as you go through the radio, you're actually tracking a sine wave, so that makes it a little easier. Yeah, so the whole thing revolves around a sine wave, and basically a sine wave is the actual original wave that's formulated by a generator or a electric circuit like a coil and a capacitor. With a generator, you've got your mains coming down your power lines, and that comes down to 50 hertz, and that is actually generated by a 50 hertz generator. And what happens when the generator spins around, you have a magnet on each side, and you have the rotor with coil on it, and it whizzes around, and as the coil hits the dead centre of the magnet, you get maximum output, and as it spins away from the magnets, it gets down to zero output, builds up and comes back in as maximum again. And it's the same thing with a coil and a capacitor. When you're generating an electromagnetic field with a coil and capacitor, the capacitor charges up to maximum output, discharges and recharges. So basically you end up with a sine wave.
We don't have one.
I do here.
Oh.
Okay. All right, so you basically end up with a sine wave. Is that the best one to have?
No, that's got modulation on it.
Yeah, it has. Hang on, we'll go back here.
One on the wall, on the brick wall.
Yeah, there's one. So the sine wave is generated by as I said, mechanically or electronically, and it's the peaks of the magnet or the peaks of the capacitor. So you'd start off at a neutral point about there, and so your sine wave starts off as it gets to the bottom of the discharge cycle. It then, I'll start it off here. It's easier here. So you start off at that neutral area there, and then as the magnets get closer and closer to the coil, you get your peak output. And then it decreases as it goes away from the magnets, and then it ends up there. So that's one sine wave, and that's what's generated down the electricity lines, and that's at 50 hertz. And the same thing happens with a capacitor. Now the thing about the electronics of a 50 hertz sine wave or 50 hertz generation electricity, the electromagnetic field actually follows the inside of the conductors to your house. If that was generated at 1,000 kilocycles per second, and I think the bearings in the motor would be pretty hot, running hot, but if it was generated at 1,000 cycles per second, kilocycles per second, that electromagnetic field would not like to run down the centre of that wire. It would like to run along the surface, and it's called a skin effect. And once it's on the surface, it would like to radiate. So that's a different characteristics you get in the frequency of electromagnetic fields. You get to where the radio stations are. say around about 1,000 kilocycles, and they radiate, and then you get up to 2 or 3 megs, and you get into short wave, and those frequencies like to bounce off the ionosphere until they get around the world. So frequencies themselves have different characteristics. Let me go back. Okay, so the circuit we're going to go through is this radio here. That one up? No. Hang on.
That's it.
Okay, so this is the one we're going to go through. It's a H&B 6151. Actually, that's not actually the circuit. The circuit's down here. It's a 6151. It's a 1950s circuit. This one here actually uses a Hartley oscillator, and Hartley oscillator's always got a centre tap that goes to the cathode. You can easily recognise it. It's not 2 separate coils. It's a good radio. It has independent bias resistors for each valve, which makes each valve run in its sweet spot, whereas back biases are compromised. They might use -3 volts for all those valves, and insensitivities are compromised back bias. So that's the basic radio there. When I was doing this, I realised I hadn't done a radio right throughout. I've used it for the converter stage, and I do remember doing an alignment on a wideband tuner, and I certainly used the oscilloscope for that. But when I was doing this radio, I could not get the oscilloscope to work on the output of the anode to show the 455 kilohertz sine wave, and I thought, what the hell's going on? And I got another oscilloscope at home, which is very handy because it's also got a built-in frequency counter, so it tells you what the frequency you're reading. And it was showing me I was reading a frequency of 900 hertz on the anode, not 455, which I still can't explain because you got your first IF transformer just there, and that's actually a parallel tuned circuit there, and that will only accept 455, and the other frequencies that are generated through the mixing are rejected by that IF transformer. So you should be able to put an instrument on there and get 455, but I couldn't. And Ray Hoskins rang me last night when I was still in panic mode, and I told him about it. He said, "Oh, that can't be right." And I said, "Well, you get a radio out," because he lives halfway out at Geelong. I said, "You get a radio out and you see how you go." He rang me back an hour later. He said, "You did right. I can't get it to do it either." I said, "Well, that's great." I said, "Well, what am I supposed to do now?" He said, "I'm not a bloody engineer. Figure it out yourself." And I said, "In your lifetime, you've never ever tried to use a scope in that spot?" And he said, "No, I haven't." So I said, the only thing I could think of was to make sure I could get 455 on there, it was to stop the oscillator from running and shorting it out, and then injecting 455 onto the grid of the converter valve. And then, of course, 455 has to come out of there because there's no mixing, and you'll get 455 out. And thank God I was correct in that because it did work. Yeah, so if you look at the circuit here, that's the converter valve, and you can see that the frequencies that come out of the mixing, you'll get, if you've got 1,000 cycles input to the grid, say that you station 1,000 cycles coming in. Well, when it goes through the mixer, it comes out with 1,000 cycles out there, it comes out with 1,455 cycles, comes out there, 45 kilocycles comes out there, and then the sum of the above, 2,455, will also come out of there. But that shouldn't matter because it comes through here and that rejects all the others and you get your 455. So theoretically, you should have the 455, but I couldn't make it without doing it my way. So that's that. The other thing we'll show you is you really can't use the oscilloscope live on the radio because what it produces in the way of waveforms is virtually useless to do anything with. We'll show you now.
With the sound, not live.
Hey?
With the voice coming out of it.
No, I mean using the actual radio. Yeah, live. Yeah.
Where do we want it?
Okay, so if we go to the first one, which will be pin 7. Pin 7 up here. Actually, we could up here.
No, hang on, this is the oscillator at this
No,
end.
we don't want the oscillator.
You want pin 7?
Yeah, pin 7, yep.
No, that's number 1.
There,
That's pin 7 there.
Yep.
Right. We've got nothing.
Okay, so you've got pin 7. You'll have to, hang on. Yeah, we're taking a bit of a risk doing this live, but anyway, we'll give it a go. Okay, so you're on pin 7. You want your sweeps set to 1 millisecond, 4.1 millisecond.
Well, that's 0.1 millisecond.
Okay, and then your volts division, 2 volts.
0.2.
Or 0.2, I mean.
0.2.
Yeah.
What are we looking for? Audio.
Yep, we're looking for audio.
We had it before.
You had it before, yeah. So you got pin 7 there. Okay.
Yeah, well, clockwise, pin 7.
Yeah, that's pin 7. You got that one there?
Do we have to increase the volume?
Oh, that's right.
Turn the volume up.
That's all right. Yeah, Graham turned down the volume and he told me about it and I said, I've got to remember that. And of course I didn't bloody remember, did I? Yeah.
Well, let's...
Yeah, so get a station. Okay, so that's exactly what you see on the anode of the first 6A V6, and that's your audio coming through, and it's singing, so it's worse. It goes a bit slower when there's voice. So you can't do anything with that signal. I mean, what does that tell you? The only good thing about it, if you wanted to see if your radio was working, you could race along and say, oh yeah, this is working because I can see that's working, and you could go back through the stages, that's all. But if something went wrong, you can't analyse anything in that. So that's what it looks like there on pin 7 in the audio stage. I think we'll go from there back, we'll go to pin set, go to that pin there, to the RF stage.
And it stops.
Yeah, okay. Okay, so have you got a signal there? Yeah, that's it. Yeah, you got it. Yeah, what you're seeing there, well, you were seeing it. Can you slow it down?
That's supposed to be the modulated signal.
Yeah, I don't know what you get the black lines for. How come you get the black lines? Yeah. Anyway, that's on the anode of the converter valve, and that's the RF signal you're getting, and that's what they call an envelope. And in between, you got the frequency, and running at the top of the envelope is actually the audio. Okay. I thought we had better lines than that. You know where it came into all the lines. Yeah, go back. No, go the other way. Yeah, go back. Keep going.
Yeah, but that'll show you the carrier.
Yeah, that's all right.
That's the carrier.
Yeah, that's what we want to see, the carrier.
Doesn't look like a sine wave anymore.
No, that's okay. No, you're picking up the oscillator. Yeah. Okay, but anyways, as you can see, that envelope is the carrier. And you can't do much with that either, except say, oh yeah, it's there. So that's it, as far as that goes. Now we'll go to the oscillator. Whack it onto that pin there. Yeah, dial it down a bit. Okay, so what we're looking at there, and this is where the oscilloscope is very valuable, that's actually showing you the oscillator frequency. It's proving that the oscillator is working, and you can also see the amplitude of that oscillator. That's on a 2 volt scale there. So 2, 4, 6 or 8 volts there on the oscillator. The oscillators usually work around about 10 average, but they can easily be 15 or they can be 8. And so it can be very important to know what the output of your oscillator is, because if you're only getting 2 or 3 volts, you'll wonder why your radio is so sick. So with the oscilloscope, you can do something that you can't do with a multimeter. You can actually look at the waveform. You can measure the waveform so that you know the output of your oscillator. And if you scroll the tuning gang, it's been scrolled across the dial, and you'll see that the amplitude of that oscillator isn't varying much at all. It's very stable. So you can say to yourself, well, gee, the oscillator on this is working very well. Usually if you go down to the lower end of the frequency, the amplitude of that oscillator will actually drop a bit, but this one drops virtually none at all. So the oscillator is tracking very well. You know that any point on the dial, you're getting maximum amplitude out of it. And that helps too. So that's the thing that you can do with an oscilloscope that you can't do with anything else. If you've got an Armstrong oscillator, well, that's 2 coils. You can usually measure the output of the oscillator, which is around about 10 volts. But being a Hartley oscillator, no, the only way you can actually get to see it and measure it is to use an oscilloscope. So there's a big advantage there. Okay, so that covers the oscillator in general. Oh, just on fault finding, while we're looking at it. Okay, so that's the radio circuit. That's the Hartley oscillator. If that oscillator is not working, I mean, you check your voltage. It could be that capacitor there is open circuit or shorted circuit. We don't have a circuit. Hey?
We're going to put a circuit up, which is
a
capacitor. We don't know which capacitor.
Oh, something's gone wrong.
Yeah. We're out of sync.
Oh, here we go. All right. So if you didn't get that waveform, it would tell you the oscillator's not working. And that could be due to the capacitors around the oscillator coil, especially those 2 there. If you short these out, and I have to test it out, the frequency wave just cuts out. You get nothing. So if they're a short, you're going to get nothing. If they're open circuit, you sometimes get, if they're leaky, you'll get part of the oscillation, but not much. And unfortunately, this is the only thing wrong with this presentation is the hardest faults are usually the ones that they haven't totally failed, and you can't display them really. So on these, if you short them out, the display the oscillator just stops oscillating. It's as simple as that. And if they're leaky, I have seen a picture of one that was supposed to be leaky, and it gives a dark line down the centre of the oscillations. So that would be the key fault you'd be looking for in the oscillator stage. And of course you'd be checking the anode oscillator resistor, the 22K, and making sure you get your 70 or 80 volts up there. So that's all right.
Where was your probe on that? Is that on the grid there, is it?
That probe, the probe there is actually on the anode, just between those 2 capacitors. That's where the probe is at the moment. That actually shows the oscillations. Is that okay? Yeah.
The valve could also be called.
Yeah, and of course you've got to check the valve. That's the obvious. Yeah, and and in fact it'd be one of the first things you'd check if the amplitude of that wave was down, say to around about 4 volts. You'd immediately check the valves as your first. Can you see where that probe is? Yeah, it's right there. Yeah, that's where the probe is, right there, and that's where you can measure the oscillation. I mean, you can put it on the other side of the capacitor if you want, but that there's a very safe spot for it. So that's that. And of course, if the oscillator coil's open, you'll have problems too. So basically, it's isolating the stage for you, just like most test instruments do. What else? Yeah, that's about it. So what we'll do now, we're going to short out the oscillator, and then we're going to connect up the signal generator and then put a sine wave right through the radio and then track it through with a sine wave. Okay, now you can see the difference. Instead of seeing all those squiggly lines that we saw before, what we've done, we've injected the 455 kilohertz straight onto the grid of the converter valve, and that's being amplified and it's going straight up to the anode and being detected on the oscilloscope. Okay, so we've injected a signal, getting a sine wave out of the anode of the converter valve, and if you short out, which I have done, if you short out the IF coil here, and pretending it's got a short in it, that sine wave will collapse, and the same would happen with the capacitor. And if it goes open circuit, which I haven't tested, what I might do at the end of the presentation, we might go along there and start cutting some wires to see what happens. But if it's short circuit, yeah, it collapses, and the same with the capacitor. Okay, so we see the sine wave there, and we can see, yeah, if this goes faulty, it would show up. We should go to the next stage, which is pin 1 of the 6BA6, which is just on the other side of the IF transformer. Yeah. Got it. Yeah. Now, yeah, we should pick up that sine wave again.
There we go.
You got it? Good show. Now, this sine wave is... Oh, you got it there.
It's coming.
Oh, it's coming. Okay.
There.
Yeah. Okay, so that sine wave is quite a big drop in amplitude compared to the one you just saw on the anode, and that's due to the loss in the IF transformer as it's being transferred. So you'll always get a drop. If we had two sine waves side by side, it'd expose the drop, but I think the per scale on that would be lower than the previous stage. Anyway, you get quite a bit of a loss actually when you go through an IF transformer. Anyway, so you can see the sine waves there, and it's nice and clear. If it wasn't clear, you would know there's something wrong either in the IF transformer, which would be the main culprit, or you might even have a problem with the feedback capacitor that comes off the anode back down into the grid. So that, as I said, if you short it out, yeah, it disappears, because I tried that. Okay, so now we'll move on to, okay, so we're on the grid, and we go to the anode of the 6BA6, which is pin 5. Actually, what I could, oh no, I'll finish it. Because while we're on that previous valve, on the grid of that previous valve, the 6BA6.
I can change it.
Yeah, okay, change it, and we'll try it. Because while you're there, you can actually do an IF alignment on it, and it's quite accurate. Unlike when you do a normal alignment, you always have to align the last IF, or which way you look at the circuit. But you do the IF that's closest to the audio stage, because if that's faulty, you really can't do the first IF. So you always do that one first. But in this instance, you don't have to do that, because you're actually the signal is actually at the first IF. So you can do that. So here we're actually looking at the IF signal of the, gee whiz, a bit dark in here. I'm going to try and tune the IF.
I'll give it a go.
Yeah, see that? Screw it down. Yeah.
Down?
Yeah, go down.
There we go.
Yeah, you can see the amplitude starting to change. Well,
Turn it a different way?
You turn it the other way, the amplitude actually comes up. So you can tune it to the exact amplitude of the actual signal itself. So you can actually align the IF. There you go, you can see it coming up now, see that?
Nearly off the screen.
Yeah, it's nearly off the screen.
There it is, there's the peak.
Yeah, so wind it back down again so it goes down, back down again.
Oh, hang on, I've got to find the slot.
Yeah, right.
The screwdriver keeps falling off.
Oh no, it's yeah, there you go. You can see the quite a dramatic change in the amplitude, but that's how easy it is to align the IF, and it's a very accurate alignment. So you can use that to align the IF.
Beautiful.
Okay, so now we'll go to pin. Yeah, we'll go to the anode, pin 5 of the 6BA6. Okay, now it's massive. The output of the second IF valve is huge. So just as a quick guide, you move it from one to the other, you can tell straight away that the valve is amplifying. So that stage seems to be all right. Okay. All right, so we're on there. You can see it's amplified, so that's okay. Okay, so you're out here again. If you shorted out the primary winding of that IF, yes, you'd lose it. Also, if the screen resistor went open circuit, you would also lose it, the sine wave. And if the 0.05 capacitor shorted out, you would certainly lose the sine wave as well.
They normally go leaky.
Yeah, they quite often go leaky, and also one of the key components for causing motor boating. So your sine wave would be probably going put if it was leaking.
How was that?
But. Yeah, so it would put. Actually, it's interesting. I shorted the bias resistor out, and the sine wave didn't disappear. It stayed there. We went down a fraction, but it basically stayed there. So I'm presuming that the AGC compensated for the loss of that bias, back bias, the cathode bias resistor, because the sine wave actually stayed. All right, so we'll go to the next stage now, where we go to pin. Which one? 6BA6 anode. We've just done that. Yeah, if we go to the IF transformer, which then goes to pin 5 of the 6AV6, which is actually the input of the diode. What I'll do, do that. All right. So at the moment we've got just a carrier wave, which has got no information on it. The only good thing that's for is Morse code. So we'll just put a little bit of modulation on. You can see, because the modulation is only one tone and it's about 400 hertz, but you can see the actual modulation.
Or it looks like that.
Yeah, that's the modulation there. You can see the audio signal sitting on top of the carrier signal. I'll show you. I've got a picture of it here that might be better. So we got the sine wave, and I've modulated it with the 400 hertz tone. And on this picture, you can see how the peak down the bottom has widened out because the modulation sitting on top of it. It's actually probably increased the amplitude of the sine wave from about there up to there. So in fact, we've got two signals here. We've got the carrier signal at 455, and we got the audio 400 hertz sitting on top of it. So if we can get rid of the RF signal and just be left with the top of it, which is the audio signal, we can separate the two. Well, we're on the way to being able to listen to a radio. And looking at the sine wave there, you can clearly see what's going on. You can say to yourself, yes, the modulation's coming through. I can see it there, and you can actually measure the amplitude of the signal. Right. Okay, so we'll go to the next one. which is, that was going to go to that diode. That is, that's pin 5 of the 6AV6. Yeah, try microseconds. Are you getting a sine wave?
So I'm getting the modulated signal.
Yeah, okay.
That's the carrier.
Yeah, okay. You got that?
And that's the recovered audio.
Yeah, that's right. It is the recovered audio. So yeah, okay. Yeah, you're right.
The carrier shouldn't be there.
Hey?
I don't think the carrier should be there. Anyway.
Yeah, it does. It's going into the diode. It hasn't come out of the diode. It's going into the diode. It goes.
Okay.
Yeah, it's just going in, right? Now, if you put it to, hey? Yeah. Yeah. It is. It has taken of the top. It's true. So it's half detected. If you go to the pin, I think pin 1. Go to pin 1.
Pin 1 is the grid.
Yep, pin 1.
I'll have to turn up the volume.
Yeah, try that.
Not much there.
Hey,
It's running flat out.
that's flat out. You've got to turn up the volume a bit more. Yeah, now you can sort of see the pattern that's coming up. And you can see it's cut off the bottom half of the sine wave after the detection. So now you've got audio with some carrier left, and the carrier that's left, you can go to the anode now. So you can actually see that happening. So we've got that, and you can see the bottom half of the carrier has been squared off, and there's audio in there. And so, going back to the circuit, so what we saw there at the 6AV6 grid input, by the way, when I was doing this, I found out there was an error in this circuit. They're using, in the circuit, they were using pin 6 as an active diode and 5 to earth, where in the radio it's actually the other way around. Not that it makes any difference to the performance, but just interesting to note. You wouldn't think they'd miss something like that. But anyway, so what we saw coming in there was half the sine wave chopped off, and the audio signal there, and half the sine wave there with RF in it. So what happens is that half sine wave comes down here, and this 100 puff capacitor that comes out across here, so the signal comes down there, around there, it comes out there. The 100 puff capacitor to earth, then that 100 puff is at RF frequency, or suitable for conducting RF frequency. So the other half of the sine wave actually disappears, and it leaves the audio sitting across that resistor, which is the volume control. So now you've virtually got pure audio left, and then that comes out of your volume control, slips up there and goes into the grid of your first audio valve. So we can go back to the anode.
Michael, you've made a bit of an error.
Did I?
The load resistor on the anode of the 6AV6, see it says 270k?
Oh yeah, yeah.
You've got a 470k. And that's maybe why the signal's distorted.
Where have I got 470k?
Where the 270k should be. So you don't have enough volts on the anode.
Ah, but the radio works all right.
Yeah, but that's why it's probably distorted.
Ah, right, okay. All right.
Yeah, you can see it there anyway.
Yeah. Oh, I'll keep that in mind.
Finger across it. No, you put your wet finger across it. Sorry, where were we going?
Okay, go to the anode.
That is the anode.
Pin 7. Are you on pin 7?
Yeah, that's what I'm on.
Oh, you're on, are you? Okay. So, what pitch have you got there at the moment?
A distorted sine wave with 50 cycle hum on it.
Let's look. Oh, yeah.
So if you probably change that resistor, see in there, that one,
Yeah.
probably round that up.
So you reckon, what's in there, 470?
There it is, look, you look at it.
Yeah.
See,
Yeah, 470k.
Yeah, it
Yeah.
should be 270, but anyway.
Oh, how about that? Found another fault. This is oscilloscope business. You know, it goes really. See, now that's what you can find that you wouldn't find normally. Now we know what happens when you put in the wrong resistor in the anode circuit. You end up with a wave like that. So that's fault finding in the real world for you. Okay, so but you'll notice there's no RF left in that signal. It's just audio, a little distorted degree, and then from then on, that audio signal then transmits to the output valve, and that then is a sine wave, and then of course it's a bigger sine wave on pin 7. There's pin 7 there on the 6M5.
You want me to go there? Pin 7?
Oh yeah, but the sine wave will just go through the roof, that's all, but you can put it there. So that's basically tracking it through with the oscilloscope. And as I said, the components around that stage, if the sine wave's not there properly, just like you just saw with that audio stage where it was distorted, and it is probably due to that resistor, because...
And it's also inverted at 180 degrees.
Yeah, I noticed that, yeah, it is.
Valves invert signal. Yes.
Yeah, that's right. Okay.
Looks like it could also have some 50 cycle hum on it.
Yeah, that was the next thing I was going to say. Now, we haven't really attacked the power supply, but about the only thing you can do on the power supply, if you put the oscilloscope on it, you should see some ripple on it. So you might want to do that, Charlie. See what you can do there.
That's straight out of the rectifier.
All right. What's it look like?
So how many volt ripple on it now?
Put your finger on it, tell me. I don't have a meter.
Doesn't it tell you on this scale?
Yeah, we've got on the half a scale, half volt, so it becomes 5 volts, and we've got how many centimetres? 1, 2, 3, 4 centimetres at 5 volts, 20 volts a ripple.
20 volts.
And if we go after the
filter?
it should all be gone, which it is. See?
It is almost gone.
Yeah, there you go. Very good
But
display
it
there.
it still does have some in there.
Yeah.
Oh, you never get rid of it all, but do you? There's always a residual amount. And if you, it's not here. If you do get that residual amount, and it is only small, but if you have a capacitor, it's quite often you see them in circuits, it'll go from the anode down to the grid as a feedback to help make the last stage a little bit more stable, get a bit of reverse feedback. But that capacitor, which is usually about 70 puff or something like that, if that ripple gets through that capacitor, it gets dumped on the grid of the output valve, and then you get some very serious hum. And I've had a couple of sets have done that, where I said, where's all this bloody hum coming from? Because it all looks okay down here. And then, of course, when you track it through, yeah, it's that little 70 puff capacitor, and it only needs the tiniest amount of hum to get through that capacitor, and it puts it on the grid and amplifies it. So yeah, so you can look at your power supply voltage just like Charlie put it there. There's about 5 volts, wasn't there, on the cathode? He just worked it out.
20.
20 was it? Oh, 20. Okay, so there was 20 volt of ripple on the cathode, and then after the filtering, that dropped down to.
Well, we've gone from that.
Yeah.
To that.
Okay, I didn't see that. Oh, you've gone from that to that. Well, that's a pretty big step. Yeah.
But there's still a bit there.
Yeah, and you will always, it's virtually impossible to get rid of that last bit of ripple. Yeah. So that's what you can actually see in your radio. So you can do exactly what we just did then. Look at it before it's fully filtered and then after it's fully filtered. And if it's not fully filtered, you say, hello, something wrong with the choke or the electrolytic, which, you know, unless you saw it on the crowd, be harder to see. Yeah, so that's about the only way through. The only thing we can do now, are there any questions at this stage? Yeah?
Just coming back to where we started off, you've still got the signal generator at 455 just going straight into the grid of the 6B6 at this stage, yeah?
Yeah, no, it's actually, well, it's going, right, but it's a modulated signal, right? So when it goes through that diode, the 455's gone. Yeah, you see, the diode detects it and takes away the RF signal, the 455, and the last half of it's left is filtered out by that 100 puff capacitor to earth. Yeah.
You're still feeding the signal generator for the front of the radio, aren't you?
Yeah, that's right, right from the front, because that audio signal would have been there right from the front. I just deliberately turned it off to make the sine wave look cleaner, that's all. Yeah, but normally that signal would be riding the back of the sine wave all the way through the set. And then when it gets to the diode, it gets separated. The diode takes the audio off the sine wave and puts it onto the valve, and the other half of the sine wave is still there. At RF frequency, gets filtered out through the 100 puff capacitor. So then the valve has only got the audio part of the signal in it.
Well, that's 2 parts.
Yeah, that's right. So the first half gets detected, taken away by the diode, and the second half gets filtered out by the 100 puff capacitor. So the only thing you've got left is that audio bit right at the top, which is pure audio, and that's what ends up inside the valve, and then it comes out of the 6AV6, of course, as pure audio. Yeah. So we started with 455, and the carrier would, in the real world, would be sitting on top of that right from the aerial. Yeah, and then being separated at the diode and that capacitor, which we've just done. Yeah. Okay. Any other questions yet?
Is the probe flat on the B plus there, or is there a capacitor in the probe?
No, it's straight on it with a by 10 probe.
Okay, so what's the voltage? A couple hundred volts?
Well, I'd say so. We don't have a multimeter, but we...
Don't make him count the squares. I must admit, I have this oscilloscope at home, and yeah, as I said, it's got a built-in frequency counter, so you know the frequency that is right, or you can read the frequency that's inside the crow, and then it's got 2 cursors that you can move up and down, so you don't have to count the squares, because once you move those cursors from the top of the sine wave to the bottom, it immediately tells you what voltage or what signal strength you've got in there, and it makes it so much easier. The only drawback of these old crows is counting those bloody squares and doing that. But what did you want to know in particular?
Well, just the crow can handle a B plus without any, like a times 10 probe, isn't it?
Yeah, well, on the vertical, it goes up to 20 volts per division. So when you put the by 10 probe in, it becomes 200. So it's got 8 centimetres of deflection, so 1600 volts you can put into it.
So the crow will actually take how much? 600.
1600.
1600, yeah.
Yeah, well.
Yeah. Okay,
Maybe the oscilloscope might not even handle 1600 volts across the input.
Probably not.
The protection diodes might short out.
Yeah. Any other questions down the back? Yeah.
In this case, the crow's AC coupled.
Yes, it is AC coupled. Otherwise, it would be off the screen up there somewhere with the ripple on top of it.
Geez, I'm glad you answered that question. I knew you would come handy. I knew you would.
That's the idea, the AC-DC switch on the input.
Yeah.
DC
Yeah.
actually gets you your levels.
Yeah.
And AC disconnects the DC component and only lets the AC
Through.
display. So
Yeah, well, just as a general calibration for your own oscilloscope, if you were to put the trace in the middle of the screen, and if you had a by 1 probe, you could get yourself a 1.5 volt battery and put it across the terminals, and the trace should move up 3 squares. And then, of course, if you reverse the battery, it should move down 3 squares.
correct.
That's if you've wired the oscilloscope correctly inside. Because sometimes if you put the plates around the wrong way, it'll go in the opposite direction. And then the other thing should be is every time you turn the shift control, turning it clockwise should make the trace go up, turning it anti-clockwise should make the trace go down. Because when I was at BWD, I occasionally wired them the wrong way, and you had to turn them. But sometimes you could correct for it, but then of course when you checked it with the battery, it looked right, but it was doing all the wrong things.
Yeah, so we've done the radio, we've done the power supply.
Tell them not to touch the mains like you did before.
Oh yeah, don't do what I did before. I lifted up the chassis and got a nice little shock off it.
That was his energy for giving the speech.
Yeah, I got a bit of a charge up there. Yeah. How shouldn't you hear that?
Tuning the second IF, well, it's going to have the same result as tuning the first.
Well, we can do that. We can try that. Yeah, just put it on the. Which side do you want tuned? The primary or the secondary? I'll do the primary first.
But the problem is, see, when you put the probe on, it's going to have some capacitance.
Yeah.
And it's going to change the frequency. So when you peak it, it's still not going to be right.
Nah, it'll be fairly close. I know, and the reason I know that because I actually put a frequency counter on it to check it.
You can do it for the grid of 675, that's the audio output.
Yeah. What do you want to do with that?
Just stick it on the grid of the audio output pentode, and that will give you an amplitude which, when you adjust it, you get it.
Oh yeah, you can do that, or you can put it straight on.
Because even listen, look, just by putting the probe on.
Yeah, it's just that at the IF stage you'll see the difference in the peak a lot better than you will at the 6M5 in this instance because you're right on it.
Yeah, because see, if the probe has got 3 puff capacitance across the 100 puff on the tuned circuit, it's out by 3%, and you can hear that when you take it off.
Yeah, it's loading the circuit. What if you put it on by 10?
It is by 10.
Oh, you're on 10, eh?
One, it would stop.
Yeah, I thought that might be the case. You're on 10. That's okay. All right. Well, yes, you can hear the loading, but there's no reason why.
That's by 1.
Yeah, but you can hear the loading, but it doesn't mean it's going to change the frequency.
It will.
You sure?
Yes.
All right. Yeah.
Not that I would do this. I've got 3 bays at home.
Yeah.
The sine wave of your AC coming in at 50 hertz. I often wonder with all these people that got all these solar panels around our suburbs now, if that's interrupting the natural sine wave. I wonder if that's take the chops and the chops.
Oh, it could do. Yeah, if you looked at your sine wave board with all that interference on it, yeah, it could make a difference. Yeah. Although the 50 hertz on the mains would be pretty strong 50 hertz. Yeah.
There we go, Michael. Look.
All right. Oh.
Winding it down.
If you adjust that, adjust the what's the name because you're getting a second signal on it. Just
Time base.
Yeah, the time base. Yeah, that's it. The centre knob. Yeah, there you go. There you go. Okay. Yeah, there you go. You can see it getting. Well, I'm getting into the light rather than getting out of it.
That's about the best we can do.
Yeah, wind it down again so we can see the difference. Yeah, see it's come right down now. And then he's winding it back up again. So it works. Is that on the primary or the secondary?
That was the primary.
Oh, the primary, the top one, yeah. Well, there you go, woman, just for you, the top one. Get your rocks off on that. Now, where are we?
I'm sitting down here.
Okay, so anything else we can do while we've got it in that mode? Any further questions? No?
We've confused them.
Yeah, so, yeah, we've confused them all. All right, and so there's no point in going back and cutting out wires because the sine wave actually isolates it to a particular stage anyway, and you're really looking at the components in a particular stage. But the biggest advantage I find of using the oscilloscope is definitely in the oscillator stage, because I can find out what the output is straight away. I can see if the oscillator's tracking straight away properly, and it's a big benefit. Yeah, and if I do have distortion that I have problem with in the audio stage, I would just put in a 400 hertz signal or a 1000 hertz audio signal straight onto the grids of the audio stage and trace it back there to make sure that what the sine wave looks like, and I'd use that to help me out. That's the way I would do that. But oscilloscopes, they are good fun, and you can have a good time with them, and they aren't expensive. And if anybody wants to buy a nice oscilloscope, dual wave, 15 megahertz bandwidth, you can buy this one here. Yeah, this one you just saw in operation, which proves how well it works. So that's about all, I think. The idea, it gives you a feel of how to go about it, and that you can find faults, just like we found that resistor that was high, 470k instead of 270k. Geez, I'm glad you saw that, spotted that. But sure enough, the reason it was spotted was because the reason I looked is because I saw the... Yeah, that's exactly what I was going to say. he could see the distortion on the output of the 6AV6, and that made him look, and he found the fault. So there's a classical example. Yet when you listen to that radio, it doesn't sound distorted. But
to your ears.
To my ears, yeah. Well, at this age, what do you expect? Yeah, so, I can't see anything else. No other further questions? No. No? Well, that's fine. So we'll call that quits, and hope it's encouraged someone to have a bit of a play. The one that would have stopped a lot of people, and it really stopped me in the tracks, was the fact that I couldn't get the 455 kilohertz signal on the anode of the converter valve. But once it's easy to overcome. You just short out the coil, the oscillator coil, and put the 455s directly onto to the grid of the valve. Yeah. Okay, so that's it. Thanks for your attention. All right.
About 97 something, and since I left BWD in about 1974, I had never seen one. So anyway, I pulled it to bits. I managed to make up all the printed circuit boards and everything else inside, but I wasn't quite sure of where some of the wires went, because the location of the wires is very important where you put them. If you swing one wire from one side to the other, it can take off. So I wasn't sure, and I tied some of them up with little cable ties, and then when I saw Graham's one, doesn't have any cable ties in it, so I had to reroute them all. This oscilloscope here looks very similar to this oscilloscope, but this oscilloscope is 15x, this oscilloscope is 50x. This one is pretty light in comparison to this one here, because as things get newer, they become smaller and lighter and even better performance. So that's about it. I don't know what else I can tell you about it.
Did you get yours going, Charlie? Did you get actually one going?
Not as yet. They're all sort of at the same stage. I'm doing the same little bits and things. And I've been looking for some pink wire, because I can't find any pink wire. But one of our lovely gentlemen has donated a little bit to me. Because for some reason I'm trying to make it as close as I can to the original thing. And some of the wires I've even had to join. A piece of black and white, a little joiner, and then it continues along to black and white, because you can't buy black and white. Yeah. You can't buy any, you can only buy sort of the primary ones. Yeah. So I've been struggling now probably for about 5 years to build these things, but slowly, after building the printed circuit boards, I'm now working on the attenuators, and I've had a bit of trouble finding NPO or NP0 capacitors. I've been told they're not NPO, because I was a letter and 0 is the number. Yeah, so that's about it. So we're slowly getting there, and that's it. This microphone's a little bit, needs a shake now and then. I think it must charge the capacitor to shake it. Anyway, so that's about it. I have a question.
What are you going to do with 11 scopes?
Just look at it. Because unfortunately, trying to sell it, people said, why don't you sell them? And I said, if I put 1,000 hours into each one, I said, I just can't sort of. That's the one I had trouble getting a power transformer for. That's the one I had trouble doing the attenuator. That's the one, yeah. So that's another question.
The NPOs are only 100 picofarad and below. Anything above that is not NPO.
Well, some of them are marked NPO, because they have the little black, the little black, yeah. So I needed some 220 puff NPOs, and I've had difficulty in finding them. And there's lots of little bits. There's lots of little bits in there I have been able to find. Like I need 95 puff capacitors. And because they're used in the time bus, you've got your 95 puff capacitor, and then you put a 10 puff trigger across it. So then when you go up to the 1 megahertz and you're doing the calibration across with your pulses across the front of the gravity, you twiddle your little trimmer till the 10th pulse lights up. And there's a few little things like that. Like even things like, what was the other value? 75 puff or something, you know, the other values, but not the value that is sort of, I don't know, I guess BWD uses strange values. And I've had trouble getting resistors, like resistors in the attenuator. I need things like 111K, well, you can't buy them. Well, you can, but I haven't been able to find them. So therefore you've got to get 110K, and then I put them on my digital multimeter and say that one's a little bit further that way, that's a little bit further that way, and 333Ks. You get 330Ks, but not 333s. And 10.1Ks, you get a 10K, you get selected to 10.1.
Many years ago, Charlie, I bought some hookup cable from J-Car, and of course it was just crap. You put a soldering iron near the
plastic sheet.
Yeah, away so quick, it wasn't funny. And you know, I'm pretty conservative to think about things like that, but it is very hard now, as you're going through scrap and just in the right time, the right place, to find any decent hookup wire. It's very, I don't know if people have got places where they go.
Yeah. Orban has.
Ultronics sells really good stuff.
Do they?
Yeah, they sell silicon covered wire and all that sort of thing. So,
oh, really?
But then that's hard to strip.
It's not that hard.
If you look at some of the washing machines that are put on Nature's Supermarket, you quite often find some good wiring in some of them.
I'll tell you one thing that's been the savior for me is the men's shed. They got stuff down there, a lot of the men's shed that you will never use. And they got a lot of pink wire. I should have a chat with you later.
Okay.
I'm the same way. I got to have some segregation. Well, you don't know what you've done, you know.
Yeah. Well, it's like we're trying to make them look like a good thing, you know what I mean? You know, because otherwise, you know, before you know them, you look at roommates, you know, everything in them will be different. So I'm trying to make everyone look the same. Trying. Anyway, but that's about it for me. So, the next person, yes.
The actual design engineer or engineers, are you still in contact with them, or what's the history of
Unfortunately, John Beasley passed away in 1997. And he's the man that did all the work, and he was the man that, I don't know, he didn't put his hands to it, it didn't work. You know, when I was there, we had a few engineers with all these letters after their names, member of this and member of that, but believe it or not, none of them were any good for anything. You know, like I had one gentleman that came to me once, he was only new there, and he was working on a double balanced mixer, and he came to me with a resistor. He says, "Oh, Charlie, can you tell me what value this resistor is?" And I looked at him and he said, "I don't know how to read resistors." I said, "It's a 10K. He said, "How'd you work out that so quickly?" I said, "Mate, I said, you have 1,000 resistors with 1 10K and they're off-road in a couple of seconds."
Unbelievable.
Well, his logic was that he didn't need to know how to read resistors. Because he could do things that other people couldn't, or whatever. But I found in the time he was there, he did nothing. But unfortunately, they still needed these type of people because John Beasley wasn't an engineer. He was a draftsman. And he also used to work for Morris. So somebody said to me, "If you've got a Morris 1000, the pedals are so close together because John Beasley designed them." And he just picked this up. You know, he worked in, when he was in England, he worked for a bank, I think, and they sent him to Australia to sort out some of the problems on their oscilloscopes, and before you know it, he was building his own.
That's the day he doing it.
And he was good at his job, you know, he was fantastic. He just, I don't know, he just had the knack, you know, he'd draw something up. In fact, one day when I was there, he asked me to stay back and do a stock tape for him, because I used to work with him. And we were in the store one day and we found these double-beam oscilloscope tubes made by GE. And John looked at them and he said, "What the hell are we doing with these?" No, I better not say that because he never swore. And he said, "There's 20 of them here." So within 2 days he designed a circuit. Within about a month we had built 20 oscilloscopes just to get rid of the tubes. You know, that's how fantastic he was. Because he basically said to me, "Charlie, all you really need to know is Ohm's law." He says, "If you know Ohm's law," he says, "you can build anything." He says, "You've got 10 volts, you've got 10K resistor in there." He says, 1 milliamp flows through it. He says, "On the divider for the base," he says, "you've got 1 meg at the top, 100K at the bottom." And he says, "You don't have to use an emitter resistor. And it will work, it will amplify." He says, "You put a signal in there and 10 times as much will come out the other end." Anyway, so that was that. Okay, well, thank you very much.